Alright, so the last set of notes, I set up this new method, the 7.5, where we're applications of optimization with constraints. Alright, and we're going to solve these using the Lagrange multiplier, and again, I use the Lagrange equation, which again, make sure you know it's different than what the book does. Alright, so my method is slightly different to what the book does. Alright, I'm actually going to split these applications up into the first set, which is the video today, is going to be ones where we can solve it with a matrix, which is why I use the method I use. Most of ours are that way, and the equation that we use is conducive to that. And then the next set of video will be a case where you can't solve it with a matrix, and we'll get to that in the next set of notes. Alright, so these are all applications of optimization where I have to use the Lagrange multiplier. Alright, so this equation involves a farmer. Alright, where we're given the profit per square foot of cropland, so this is profit per square foot, where X is the amount spent on labor, so he spends so much on labor per square foot, and Y is the amount he spends on fertilizer per square foot. And then he has a budget. Alright, his budget is he allocates $31.90 to spend on 1 square foot of cropland, which he has to split between labor and fertilizer, and he has to figure, well, how should he split that $31.90 to optimize his profit equation. Alright, and so we do, for these applications, have to find the constraint equations, but they're usually fairly straightforward and always linear. Alright, so the constraint equation is what's limiting us. Well, we have $31.90 to spend on labor and fertilizer, and so the constraint equation is labor plus fertilizer. The amount spent on each of those has to total exactly $31.90. There's the constraint equation, which we usually set that equal to 0 because that's the part that we use, right? This is our limiting factor, so move it to the other side, so it's x plus y minus the $31.90, set equal to 0 because that's the expression I use in my Lagrange equation. Alright, so now we're going to find the optimum profit within our constraint and go from there. So the first thing I'm going to write down is my Lagrange formula. Remember, the Lagrange formula, the first part of it is the original equation, which is that profit. So I'm going to rewrite the profit that they gave us. Make sure I write it down correctly. And then it's plus the lambda variable, right, the Lagrange variable, times the constraint equation where we've set it equal to the part where we've set it equal to 0. Alright. And there's the formulation of it. Alright, so that's the equation I'm going to use and optimize. Alright, so there is my Lagrange formula. Now my 3 partial derivatives, which we talked about yesterday, but they're pretty straightforward. Right? My partial derivative with respect to x, what's the derivative of the profit equation with respect to x? And so I just look at the x part. So the first one I got is negative 2x. That one doesn't have an x value, it zeroes out. The derivative of xy with respect to x is y. Then I have a 4x, I get plus 4. Zeros away, zeros away. Alright, so there's the derivative of the profit with respect to x. Then we add lambda times the derivative of the constraint with respect to x. Well, the only x value in the constraint is x, and the derivative of just x is 1. I'm going to write it down just so that we know I took the derivative, and then set it equal to 0, because remember, everything that we do, matrix and everything that we use, only works when I set it equal to 0. So I just go ahead and do it there so you don't forget. Alright, now the derivative with respect to y. So same thing, I take the derivative of the profit equation with respect to y. So just the derivative of all of the y parts. So the x squared zeroes out. Negative 5y squared is going to give me a negative 10y. Derivative of xy with respect to y gives me an x. 4x zeroes out. Derivative of 2y is 2. The 1100 zeroes away. Alright, so there's the derivative of the profit. Plus lambda times the derivative of the constraint, which again only has a single y value. So the derivative of the constraint equation with respect to y is 1, and again set it equal to 0. Remember, the derivative with respect to lambda is always the constraint equation, because the derivative of lambda is 1 times the constraint equation. So I just go ahead and write down the constraint equation, because that's what it is, and set it equal to 0. Alright, there is my system. It is a linear case, which means I can write it in the form ax plus by plus c lambda equals some constant. Alright, so again, the biggest thing is make sure it's in the right order. X, then y, then lambda, and if there's any constant, it has to be moved over to the other side. And all of these do have a constant I'll have to move over. In the first one, I have my -4. Alright, my -4 is going to be moved over to the other side. And so -2x plus y plus lambda equals -4. In my second equation, I've got the constant 2, so it needs to be moved over. So again, I'm going to subtract 2. Reorder it, make sure x first. So x, and then the -10y plus lambda equals -2. And then the last one is just the constraint equation, right? I moved the 31.9 to the other side. And so it's x plus y, no lambda, equals the 31.9, which is my constraint equation. Alright, so there's my system that I can now plug into my matrix. So again, show what you're plugging in so I know what method you're using. Alright, now I'll know in this case for sure if you've watched the video or read the book, because the book doesn't use this method. Alright, then you row reduce, which you do your RREF. You get your nice row reduced matrix that gives me 20, 11.9, and -83. Alright, so my x value is 20, my y value is 11.9, and my lambda is 83. Again, we find lambda, we don't do anything with it. Those are the two that I want. And so remember, x is the amount spent on labor, so it's dollars per square foot, right? If I go do my units, dollars per square foot. And so we spend $20 per square foot, or per foot square, on labor. And we spend $11.90 per square foot on fertilizer. And if you notice, those two things add up to the 31.9, and they should, right? Because I need to only spend $31.90. Well, 20 plus $11.90 adds up to $31, so it kind of checks. Alright, then the profit. Well, the profit is I go back to my original profit equation. So I go back up here, my original profit equation, and plug in my value. So again, I take my profit equation, plug in 20 for x, 11.9 for y, and so again, you plug it in. Just make sure you're really careful. I'm going to assume you guys can plug it in. You should always double check me though, because sometimes I mistype a negative or mistype it in, so always a good rule of thumb to double check my numbers. 275.75, which again, make sure you give the unit, so the amount of profit is not just $275.75. That's how much it is per square foot of cropland. Alright, and there is my solution. Alright, so like I said, these problems really aren't horrible if you have the method down, right? Because the algebra is all done on the calculator. Alright, the next example. A carpenter makes two different kinds of tables. Alright, a small table which represents the x value, and a large table which represents the y value. The profit equation is given by that equation there. Alright, the carpenter, spit it out, would like to optimize his profit, alright, but his budget limits him to the numbers of tables he can build. Each small table costs him $100 in material, each large table costs him $200 in material, and his budget is $16,500. And so this one's a little more to the constraint equation, right? Because my x represents the small tables, right? And they cost this amount. Y represents the big tables, and they cost more because they're larger. And then he can spend up to $16,500. And so technically speaking, the constraint equation is less than or equal to that amount. But we do typically just write equal to, although we will do a couple of examples where it's important to remember that it's actually less than or equal to. Alright, so it costs us $100 for every small table, so the cost for small tables is 100x. Cost for the large tables is 200y. We have a budget of, again, like I said, technically it's less than or equal to. We can spend up to or less than the 1650. We do usually write, though, equal to, just to make life easier. All right, I'm going to go ahead and set that equal to 0 because that's what we use when we set up our problem. All right, so my Lagrange function that I'll use, which I'm leaving my profit up there so I can see it. All right, so the first thing I write down is my profit equation. Kind of squeeze it in here. And then it's lambda times that constraint equation where I've set it equal to 0. So that 100x plus 200y minus our 16,500. And I barely fit it on my page, but I did. Alright, so now we've got everything that we need to find our partial derivatives and then solve. So partial derivatives with respect to x, with respect to y, and with respect to lambda. Alright, so derivative with respect to x. So basically you just take the derivative of the original equation with respect to x. And so it's negative 2x plus 25 plus y, zeros out, zeros out, zeroed out. Then lambda times the derivative of the constraint with respect to, so there's a number in front of the x, well that's the number that comes along, 100. Set it equal to 0 just because, again, it's proper to do that. And it's a key step that we want to see. Alright, now the derivative with respect to y, so with the derivative with respect to y, zeros out, that's x, right? Derivative of xy with respect to y is x minus 135 minus 0.8y, zeros away, lambda times the variable with respect to y is 200, set equal to 0. Right? And then the derivative of the Lagrange part is just 1, and then times the constraint equation. So it's 100x, 200y minus 16,500, set equal to 0. And there's my system. So once you get it set up, these linear cases aren't too bad, right? This is a linear case, which means I can put it in the form ax plus by plus c lambda equals a constant. And I do need to do that because it's what we have to plug into the matrix. And that's also to check that they are actually linear. Alright, so the first equation, I have to move the 25 over. So I subtract that 25, move it to the other side, write it in the right order, 2x plus y plus 100 lambda equals negative 25. The second equation, I have to add 135 to the other side. And so x minus 0.8y plus 200 lambda equals positive 135. And then the last one is always the constraint equation. So 100x, 200y, no lambda, equals that 16,500. Alright, so there is my system. I'm now ready to plug it in to the calculator. And just make sure you're careful. Make sure you've got them in the right order, and then you've moved variable parts over, because it matters, right? When I move them over, they have a different sign. And then just be careful typing it out. Some zeros there. Alright, then do the row reduced echelon form, and it should give you out 65, 50, 0.55. Alright, so there's the x value, there's the y value, and again we find lambda, but we're more interested in x and y. Alright, because that gives us the answer to our equation, to our question. Alright, so the question was, how many small tables, how many large tables should the carpenter build in order to optimize his profit, and then what is the optimum profit? Well, now we know. X is small, y is large, so to maximize profit, he needs to make 65 small and 50 large tables to get a profit of, well, I have to plug that in. Alright, 65 for x, 50 for y, and again, that goes back all the way up here to this original equation is what I have to plug. The 65x, right, 65, I gotta find 65x, 50y, and that goes into this equation. Alright, again, you should always double check, make sure I plug it in right. So when I plug it in, I get the profit is 2,900. This is optimum profit when he sells 65 small and 50 large. Once he's covered his costs. Remember, profit also includes covering costs. It seems kind of small, so you should always double check me. Alright, the last one. And then we still have another set of notes for this section. It's more applications, and it's kind of looking at our special case where it's not going to be linear. It's also going to be one similar to this one. Alright, so this one's actually going to come out where it matters that it's less than or equal to case. Alright, so we have two different types of bicycles. A road model and an off-road model. X is the number of road bikes. Y is the number of off-road bikes. This is total cost in dollars. Alright, suppose each road bike requires 2 hours to assemble. Each off-road requires 5 hours to assemble. They have a total of 100 hours to assemble the bikes. Alright, so again, this part gives me my constraint equation. Alright, I'm limited by time. I don't have infinite amount of time. I have 100 hours a week to assemble my bikes. Alright, so the constraint equation is 2x, right? X represents the off-road bike. 5y, so that's how much time they can spend on the off-road. That's how much time they can spend on the... Alright, so this is how much time they can spend on the road bike. Sorry, X represents the road bike. And this is how much time they can spend on the off-road bike. Alright, and it's got to be less than or equal to 100. And I'm actually going to leave the less than or equal to this case. Because it's actually going to come into play in this example. And we'll do another one like this in the next set of notes as well. Alright, first step though, move the 100 to the other side. 2x plus 5y minus 100 is going to equal to 0. This is the part that I'm going to plug into my Lagrange formula. And so again, I'm going to write it down here. I'm going to leave my cost up there. So my Lagrange formula, the first thing I write down is my cost. My original equation. And then lambda times that constraint where I've set it equal to 0. Alright, now once you've got it set up, like I said, these are pretty straightforward, but you've got to remember how to set it up. Alright, so our derivative with respect to x, derivative with respect to y, derivative with respect to lambda. Alright, x first, so take the derivative of the x part, which is going to give me 30x minus 50, zeros away, zeros away, zeros away, alright? And lambda times 2, right? Derivative of the x part is 2. Set it equal to 0. Now the derivative of the y, zeros away, 50y, minus 80, zeros away, lambda times 5, set it equal to 0, and then this is just the constraint. Set equal to 0. Alright, now I'm ready to plug it in my matrix, which I didn't leave myself a whole lot of room to do that. I'll actually have to reorder it, then plug it in my matrix. So maybe I'll write it over here. So my linears, where I'm going to reorder it. So I've got to move the 50 over, alright, so I've got to add the 50, the constant's got to go over to the other side, so my equation is 30x, there's no y, 2 lambda equals 50. The second equation, I've got to move the 80 over. There's no x, there's a 50y plus 5 lambda equals 80. And then my constraint equation is 2x plus 5y, no lambda, equals 100. Alright, so there's my system where I've rewritten it, and again, like I said, I'm going to write my matrix down here. Alright, so my matrix is, there's going to be some zeros in this one, because there's no x term in the first equation, and so it's 30, or sorry, there's no y term in the first equation, just an x term. 30, 0 for y, 2 for lambda, equals my constant 50. Next equation, there's no x, so 0 for x. 50 for y, 5 for lambda, 80 for my constant, 2, 5, 0, 100. Alright, so make sure you're careful. Make sure you put the zeros in the right places. Alright, then we row reduce echelon form, and we're going to get some fractions, which is why we have to keep in mind that constraint equation. Alright, so 11, 15.6, and negative 140. Alright, so what we get here is our x value was 11, our y value was 15.6. We did find lambda. Again, we're not going to do anything with it. We're going to deal with our x and y. Alright, so remember, x and y represents number of bikes they can assemble, right? I don't want to assemble a fraction of a bike, right? I can't assemble 15, or I don't want to assemble 15.6 bikes. And so what we do is, well, we have to round appropriately. This is kind of like when we had the inventory cost problem. Right? We had to have everything come out to nice whole numbers. Well, the same thing here. And so I've got to remember my constraint. My constraint was 2x plus 5y has to be less than or equal to 100, or I can't go over 100 hours. So 2x plus 5y, I can use all the 100 hours. In our previous examples, they always use exactly what we have. But I can't go over 100. I have exactly 100 hours, and so I can't go over 100. And so x is 11. I'm going to leave x to be 11. But y, do I round up to 16, or do I round down to 15? Well, I've got to make sure whatever I round to still works in the original constraint equation. Alright, so if I round up to 16, my x is 11, my y I rounded to 16, and so when I simplify that, I multiply that out, it comes out to 102. Well, that doesn't work because it's not less than 100. Alright, so I can't round to 16. Alright, we'll check out 15. You should make sure 15 works. So I put my 11 in for x, 15 in for y, multiply and simplify. That comes out to 97. Well, that works. Right? 97 is less. So basically, there's 3 extra hours where they're not doing anything because they can't complete their bikes efficiently in order to cut down in cost. All right. So that's what we're stuck with. All right. 97 is the best we can do. So that means we can assemble 11 road bikes, 15 off-road bikes. Alright, and we will minimize cost. So you plug those into the cost equation, and then plug the 15 in, not the 15.6. Alright, so you go back to the original cost equation and plug in your answer. So again, you're going to plug in 11 for x, 15 for y. So you're going to go back up here, this equation, and you're going to plug in 11 for x, 15 for y, and it's going to give you a dollar amount when you do. And again, just make sure you're careful when you type it out. When I typed it out, it came out to $390 when they make 11 road bikes and 15 off-road bikes. Alright, we'll do another example like this in the next set. So next set of notes, we're going to do 2 more. So we'll finish up chapter 7. Next time we'll do 2 more sets of notes where we'll do one example that's similar to this one where the numbers don't come out nice and pretty, and so I have to make adjustments as we go. It's going to be a little bit of variation on this one. And then we'll do an example of where I have to solve it without a matrix. Alright, and that's the next set. Alright, so again, we have 2 more problems left to finish, and that will be in the next set.